Okay, folks, so let's start with the second part about introduction to partial differential equations. And what is now my third topic of the day is to talk about the solution, but a very special solution, the so-called fundamental solution. In simple words, that is the most general solution you can obtain by solving the so-called heat equation, right? We are concentrating on the heat equation. So, third, it's what we call the fundamental solution. Well, let me assume there is I make a guess, yeah, a solution guess. Yeah, let's say I make a guess, and this solution, let's call it star, of my function dependent on, x and t of the heat equation, right? We are covering still this problem. This is the equation we are talking about, the heat equation. Let me guess, there is a function, u star, that has the following shape. First of all, it should be dimensionless. Yeah, I eliminate the dimensions out of this. And secondly, I will define a property that this solution should satisfy on top of satisfying this equation. So to make it dimensionless in general, we have a term in front, 1 over square root of dt. And then we have a function u, which is x over square root dt. So you see this function is dependent on x and t. Yeah, so we are looking, you can say we are looking for a solution of x, of a function of x and t. Well, that is true. We have x here, we have a t in there. But it is written in a way, yeah, with this x over square root of dt in front over 1 over square root dt to make it at the same time dimensionless. So I believe that maybe some solution of a function that looks like this could be a good solution guess for the heat equation. And on top, I say, well, there is the integral. If I calculate the integral from minus infinity to plus infinity of this solution, which means this right-hand side, yeah, of this solution here, xt, over x, over my space variable, I want that this integral is 1. So what is behind this assumption? Well, I suppose we have a heat source. Yeah, the heat source, let's say, is at 0. Here's my heat peak. And probably when we move to the left or to the right, yeah, x, well, the heat goes down. It's still positive. It's always positive, but the heat goes down. And what we get from this, right, is looks like a Gaussian density function. Heat is always positive. It does not cross 0. It does not go down here. And the heat source is at 0, so here's the heat peak. But when if here's the heat source, if I'm a little bit away here or here, obviously the heat is less. And the farther I'm away, if I'm here, yeah, in Reutlingen, and then I want to measure the heat in let's say, Hamburg or in Berlin, well, I promise you, the measurement from this heat source in Berlin is almost 0. So it should have a property like this. And that can be captured that all the heat points, yeah, which means the area here below this curve, if I integrate from minus infinity to plus infinity of this solution, should add up to 1. And now I look for a function u of this type that satisfies this and, in the end, this equation. So First step here is the following. Let me define and simplify my solution guess by the following variable. I introduce this variable, xi, which looks like this. It's a Greek letter, xi. And xi is defined as, x over square root dt. So what I define as xi is actually what is in here. Yeah? I say xi is x over square root dt. So let me introduce this new variable. I introduce a new variable xi. So. And now, in the next step, if I do this, I can write down this solution under this condition as follows. I can say, well, the integral then from minus infinity over plus infinity is 1 over square root dt is times the function dependent on xi, because this is my xi variable, which I already defined, x over square root dt. But then I have here dx. Well, now my function is not dependent on dx, it's dependent on dxi, so I have also to transform this. So what is the derivative if I calculate the derivative in respect of dxi? Well, this is 1, we have dxi. And the derivative in respect of x is 1, then we have dx over what is here, square root dt. So instead of dx, I bring the denominator here on this side. This is the same as square root of dt times dxi. So I have to transform the dx in xi as well, and that is this, right? Can you see this? And luckily, you see, this cancels. And what we obtain is that this integral from minus infinity to plus infinity of a function u of xi dxi, and that must be 1, right? That's still 1. We just did the variable transform. We have not changed the key point here, that it should not add up to 1. Okay. So in the end, what we have to find a function, u of xi, that is in line with this property. And if we have this function u of xi, which is this, well, then we get our overall function u of xt. So to get closer to this function, what I do next, I calculate the derivatives of my function u in respect of t. Why? Well, we know my function must satisfy this differential equation, and therefore I have to take also a closer look to what is the derivative of t and what is the derivative of u in respect of x. So I will compute the derivative in respect of t, u of t, and u of xx. And this. So I go back to my initial guess. This is my initial guess. And I calculate the derivative of this in respect of t. Well, I have to look that this guess satisfies my heat equation. Now take care. Due to this definition, this guess, you see t is here and t is here. And there's a product. You can say there's a product. So if we calculate now the derivative in respect of t, we have to use the product rule. Derivative of this, keep this constant, then we keep this constant and calculate the derivative of this. Product rule. Okay, let's do this. Well, the derivative of the first term, and we keep the second constant. Well, this brings me the 1 minus a half, yeah, in front. And then we have here, if we don't write it with a fraction, here, dt minus 3 over 2. Right? This is a half. I bring it up. The 1 minus half comes in front. Minus 1 gives me dt 1 minus 3 over 2. That's the first derivative of this. And the function u in respect of my xi remains. This is untouched. Then plus. Now we keep the first term. Can I write the first term, right? Just in this, instead of 1 over square root of dt, I can write it as dt minus 1 over 2. That's the same, like this, just in another way. And now we have to compute the derivative of this, which is, you know, that's a function of xi. You can say that is can be written in with a prime, u prime of xi. And then we have to do this in an inside derivative of t. So we have an x. We have an x. And the inside derivative, well, that brings me once again 1 minus 2 dt minus 3 over 2. Yeah, let's maybe, yeah, this together, yeah. Outside derivative, and this is the inside derivative in respect of t. X is like a constant, and then the derivative of this in the denominator, the minus 1 over 2 in front, minus 1 here is minus 3 over 2. So what we have here is now the first derivative of my guess in respect of t. Product rule, because t is here and here. For derivative in respect of x, well, that is easy, right? Because x is only popping up here. So what we have is 1 over dt times, well, the second derivative of this can be labeled as xi. And then when we have the derivative of x in respect of xi, well, the first we have square root of dt. Second, once again, 1 over square root of dt. Well, that is just then dt, 1 over dt. Because square root times square root gives me dt. Can I just write also the first part as this is dt minus 1 over 2. That's this. Then we have second derivative in respect of xi, and that can be written as dt to the power of minus 1. So I get rid of the fractions a little bit here. Now we know what we have to solve. Ut minus ux equals 0. Heat equation. Yeah, in the heat equation, if the heat equation is dimensionless, we know there is no d here. So it is in the end ut minus uxx. Well, ut is what we have here. Uxx is what we have here. So what I substitute for ut, the right-hand side, for uxx, also the right-hand side. And I factor out the common elements. So what is common? And then I make a bracket. So the common element is a factor which is dt to the power of minus 3 over 2. That is the common factor. Then what I have here, if I have factored out this, I have minus, well, let's also factor out the minus. Yeah? Then I have 1 over 2 and this term, u in respect of xi. That is from the first term. Everything else is factored out. From the second term, can you see? Here's a plus and here's a minus. If I make the minus is gone, then we have the minus here. But I factor out the minus, so I will get inside here a bracket. I have factored out this term, right? So then I have 1 over 2 u prime of xi, and take a look, what is this? This is x over square root of dt. So this, if you combine these two, this is x over square root dt. This is my xi. So I have also here, yeah, if I write this here in other letters, yeah, I can write it like this. The dt is factored out. I have the minus, I have the function, and these two is xi. That's the definition of xi. This is ut. Now I move on to ux. This here. Minus, well, which must be right. I subtract minus ux, but I have a minus here. That gives me a plus. Take a look. What we have here is dt to the power of minus over 2, dt to the power of minus 1. Well, that is dt, that is factored out. That is the whole dt to the power of minus 3 over 2. So the only term that remains is the second derivative of this function in respect of my variable xi. Heat equation, take a look, that must be equal 0. The reason why I did this, because if the heat equation is equal to 0, from this we can see what is inside the bracket must be 0. But what is inside the bracket is once again now an ordinary differential equation. We have just a function dependent on xi, on one variable. And solving ordinary differential equations is far easier to do partial differential equations. So what we see from this, that the bracket, because this is positive, right, the bracket must be 0. But the bracket can be also written in the following way. That's an even smarter way. So, did I have enough space here on the bottom? No, I don't think so. I squeeze it in here. Yeah? So what I know from this, I see that this must be 0. So, and from this I conclude, let me write what is in the bracket in the following way. This is the first derivative in respect of xi of a function u prime of xi plus u xi times xi equals 0, right? It is equal 0. So I believe that this is the same as what is here in the bracket. Why? Because I calculate the derivative of what is here in the bracket in respect of xi. Let's do this. This gives me then the second derivative, this term. Here I have a product. I calculate the derivative, well, there is a 1 over 2 missing. I calculate the derivative of this, I keep this constant, gives me this. Then I keep this and calculate the derivative of xi, which is 1, which is then 1 over 2. Can you see that this can be written like this? And from this, I see now what is here in the bracket. Yeah? Must be 0. That's even simpler, because this is a second order differential equation, and here we have now a first order differential equation. Yeah?
Can I ask you several steps before
Yeah.
when you started to write the equation ut minus xx?
Are you here?
One below,
Here?
below, yeah.
Okay.
We have to equal it to 0, but firstly we have written that ut minus d multiplied on uxx.
Yeah. Okay. So this is the heat equation in general, right? So we have this factor d. We called it S and Y, where we can get rid of this d coefficient. That is what I showed you before the bracket. So my guess already takes into account, it's a good guess, that we get rid of the dimensions. And therefore, if we take this guess and calculate the derivatives of ut and uxx, then it already satisfied the simplified heat equation where the d is not appearing. It's kind of 1 because we have eliminated the d by this good guess with this factor here in front and so on.
Okay, then next question, why don't we just write 1 instead of d? You write on the right side, d, you still use a d here.
Yeah, because I'm not specifying the d. D can be everything. Yeah, d can be an important parameter. D can be characterizing if we have a heat source, whether the heat source is in a box of air, whether the heat source is in a box of oil. Right? It depends on the density of the substance we are talking about. So d can be everything, but due to this smart guess, it does not affect, and the solution does not affect. We have not to take care about ut minus d uxx, we can write it like this. Yeah? But I know that d has an important information, therefore I want that the d is popping up in my solution. Yeah? It's just the dimension, I have eliminated it out of this here, out of this uxx term, yeah? By making this good guess. And then you can follow me to this and to this step. So, if this is equal to 0, well, what should be then this term inside the bracket? Well, if this term inside the bracket is a constant, let's call it c, or c1. If we calculate the derivative of a constant in respect of psi, it is 0. Okay, so why not suppose it is a constant, right? The derivative of a constant in respect of 0 is makes this 0. So in other words, from here it follows that u prime of psi plus 1 over 2 u of psi times psi maybe is 0, or it is, in more general, it can be a constant, because the derivative of a constant is also 0. We don't know it so far. Luckily, we'll see in a second that it is even 0, the c. Yeah? Why? Suppose about my argument here. If now we have here not x, if we write down here my psi, what can we see? If psi is 0, we have this heat source here, the peak. And here's the derivative at the peak. The first derivative is 0, right? It's the peak. So if we assume psi is 0, you see immediately this term is 0, because here stands a 0. And then what we have, what is the derivative at 0? Well, this is also 0. If this is 0 and this is 0, you see immediately, well, this requires that it's not a constant. This must be 0 as well. So that simplifies the solution even more, because now we have a homogeneous first-order differential equation. And if we find the solution for this, and we will, then we have the solution for our partial differential equation. So the question is now, what is the solution of this box? This is the first-order differential equation. It is very close to, in macro we talked about this, when we had, for instance, this LT dot over L. Yeah? Can you remember? We had an equation where we have LT, a function of t, dot over L is equal to the population growth rate. And then we moved this L on the other side, and then we got a function n times L. Yeah? Here it's not the time derivative. Here we have the space derivative. Let's call it L prime is equal to n times L. That's very close to this, right? If I move this on the other side, right, I have minus times this. We hear the first derivative, and here some term in the function. So it's very close to this. So we will get a solution similar to the population growth model we talked in macro. So let me write therefore down, let's move this on the other side to write it in the same fashion, that we have u prime of xi is equal to, then it's minus 1 over 2 u function of xi times xi. And now what we have to look for, we have to look for a function xi that is satisfying this equation. And the best candidate in all these cases is the exponential function. Yeah? Now let's take a look. Probably minus xi square over 4. That is what I think is a good solution. Well, I see this. Can you? Well, let's show you if you don't. I convince you. Calculate the derivative of this. Calculate the derivative of this guess. Well, the derivative of the exponential is the exponential. Yeah? Let's call it e. And then we do the derivative of what is in the exponent in respect of xi. Well, the 2 comes in front, cancels with the 4, then we have minus 1 over 2, and then we have 1 xi. So this is the derivative. If I plug in this here, function u times this, 1 over 2 xi. Well, that's actually what is here on the right-hand side. That means this is, yes, it is the solution of this differential equation. Yeah? Because the derivative of this is this. If I plug the derivative in here, you see the derivative is the same as what we have here. Yeah, this is my function u of xi, and here we have minus 1 over 2 xi. Okay, we got a function of xi. Well, we are not interested of u xi, right? But take a look what is xi? Xi is this, defined as x over square root of dt. So if I go back to my solution, u star function of xt, which is 1 over square root, keep some space here, dt, yeah, this, times, and this, you know, can you see this? This is u of xi, right? This is my u of xi. Well, the xi function is this exponential. That is what we already have seen here. So it's the exponential minus, and for xi, I go back here. So if I substitute in here x over dt, so we get an x square. We have this over 4, definitely. And then the square root, yeah, in the denominator is just the dt. So what we obtained here is now the fundamental solution of our heat equation. And what we see in particular is this exponential with this minus term. And this exponential with the minus term, well, we will see this has actually this Gaussian density shape. And it is a heat equation with this peak at our source, and then it smoothes down at the boundaries. I told you keep some space here in front. Why? Because it's not the full. We are not ready. One term is missing. So what we computed here is that my gas function is in line with my heat equation. What we have not checked so far, we have not checked that the integral from minus infinity to infinity of this function here, of my u theta, We have find that this integral is 1. So we have to check this. And we will see, unfortunately, when we do the integration, it is not 1. So we have to find a correction factor to make it 1. Yeah? So if I plug in this here, I have to check. That is what is not done so far. That's my last step to make the solution complete. For u, I got this nice exponential function. So let's write it right here. Xi square over 4 d xi. And the question is, what is this integral? Is this integral? It must be 1 in the end. But we will do this integral, we will calculate this integral now, and we will see that this integral, unfortunately, is not 1. It turns out to be square root of 2 pi. And if this integral is square root of 2 pi, well, how can I make this then 1? Well, if I divide on both sides, yeah, if I write here 1 over 2 square root 2 pi, and here, then this is 1. I just have to correct here by square root of 2 pi, and that is actually, I'm not sure about the 2. The pi is for sure. I think it's even 4. I think it's 4. So we will see this, yeah? So we have to do this integration. So let's question mark this solution. Yeah? So I will calculate this integral to find this correction factor that my solution, the integral over my fundamental solution, is always 1. This is what we have to check. And this, by the way, is closely linked to one of the homework question. I gave you an integral, and you will see it turns out to be the integral I was asking you. So let's calculate what is this integral. That is what we have to do. And well, if you followed statistics in the second semester, and if you work with the Gaussian distribution, it should be possible to do for everyone. It's a little bit tricky, but it is just the integration of a probability density function. Okay. Let's do this. First step, variable transformation. I define that the variable xi, and I use now a new variable, is equal to 2 times set. Okay. Let's substitute in here this. So what we get is then 4 set square. The 4 cancels with what is in the denominator, and then this integral from minus infinity to plus infinity turns into e minus set square, right? If we have 4 set square here, the 4 cancels, we have just minus set square. But take care. Now here we have to integrate over d xi. Here, well, we need then d set. So let's do the derivative of my assumption. Well, that is d xi is equal to 2 times d set. So if I have xi here, for d xi, I can write down 2 times d set. Well, the 2 is a constant. Move it immediately in front of the integral. That is 2 times this integral. So what I'm asking you now, calculate the integral of this, right? The 2 we don't care for a second. So let's define that this integral we have to care about is called I, and it's the integral from minus infinity to plus infinity, and it's minus set square d set. That is what we have to do in the end. How can we do this? Well, first we square this whole guy. Yeah, we think about I square. Yeah, I square is this integral minus infinity, plus infinity. And, well, I can write it for a second like this. This is the first times second. If I square this, I make 2 times this integral. This. Okay? I square this. This is a kind of trick what we need. And now I can write, instead of z, I can substitute, I use 2 other letters. I write a letter. I can say integration from minus infinity to y. Let's call it x squared dx times the same integral y squared dy. I just say here z is equal to x is equal to y. And in the first integral, I write it with the x letter, and the second with the y. Why not? Whenever you disagree, raise your hands. Okay, well, this can be moved together and can be written as, so we do integration, double integration, from minus infinity to plus infinity over the exponential function x squared y squared dx dy, right? I just move the integral here, bring the exponents together, and I have then dx and dy here. That's a double integral over dx dy. Okay, now we have to do this. This is now a critical step, the next one. And I promise you, this is the only way to solve and to get an integral of this or this. There is no other way. Only this. So the next is, here I see something interesting. I have 2 variables squared. That, what pops up when I see this is Pythagoras immediately. That's the only thing I have in mind. And therefore, what I have to do at that point is, I have to transform this integral into what we call polar coordinates. Polar coordinates, right? That's basic mathematics, high school. Transforming a function into polar coordinates. That's what I did, up and down it up. And so, what does this mean? Okay, can I give you a reminder? So we have here x and y on my axis. And now, the polar coordinates is plotting this coordination system onto a unit circle. There's a slope 1, and there's a circle. In a sense. So, and the radius, as you can see, of this circle is 1. So now let's plot here a line. And we know that this is the radius, and this radius, r, is 1. So here we have a distance. Let's call it x, and a distance y. This is a rectangular triangle. X squared times y squared is r squared, Pythagoras, right? That is what when I see this, then I say immediately, if I take a closer look to this integral, minus infinity plus infinity, minus infinity plus infinity, this is the exponent minus r squared, right? Because this squared times this squared is this squared, Pythagoras. But if I have now here r squared, I cannot integrate, obviously, over dx dy, right? I have to find the correspondence for dx dy. And that is what we mean by transforming into polar coordinates. Okay. So this is my x, right? The whole distance. Suppose we increase this distance by a unit dx, yeah, a little bit. Yeah, so I increase x a little bit. And then, obviously, when I increase x a little bit, I will also change my dy. Yeah? So I have here, you can say dx, and then I have here a dy, which is then modeling this change, the effect that has here. And so if I change dx, dy, I get an area here. Yeah? And now I want to find another way to express this area. This area can be also characterized because we have here an angle, let's call it theta. And this, we have this sine and cosine. You know, the sine of theta, what is the sine of theta? It is y over r. No, that is this tangent, y over x. Sine is y, that's in the opposite direction of the angle, y over r. This is y. So this can, in other words, y, yeah, can be written as, this is r times sine of theta. Okay. And now the argument is the following. If I change x a little bit, this is the same then changing r a little bit, yeah? So changing the dr a little bit. So in a sense, dr and dx is the same. And then we are interested what happens with dy. So dy from this equation is r times derivative of this in respect of theta is the cosine. Well, this is, you know, that's basic, therefore I'm fast. And then we have here the change of theta. The cosine, if the theta is very small, is 1. Yeah? The cosine at 0, if the theta is small, is 1. So what we can say and see from here, my dy can be written as r times d theta. This length is this dy, yeah, for this dy, I can write r d theta. Instead of dy, yeah, I can rewrite dy r d theta, because the cosine for theta almost 0, very small, is 1. And yeah, that gives me the change in respect here of dx, or in my case, if I change dr. So dx and dr, yeah, instead of dx, I can write dr. Now I have transformed this integral into polar coordinates. Here I have the radius squared, and for dx, we have the change in the radius, dr, right? Here's my radius, yeah? And for dy, I can write the y variable is r times the change in the angle theta. That's the transformation of this integral into polar coordinates. Well, the integration is then not from infinity, from minus infinity to infinity. Why? Because my radius starts here in 0 and can go to infinity. That's possible. And my theta integration, because it can go once in a circle, it starts also in 0, so no theta. And when it goes once, 360 degrees, that is 2 pi. It goes up to 2 pi. This integral is the same as this integral, just in polar coordinates. I do this because I can solve this, and you can't solve this on the right-hand side. Yeah? Here you can work for your lifetime until you are dead, and you will never find a solution, an explicit one. Here you will see one. Well, let's do this. I will do the following. I will first do the integration for r, and in a second step for d theta. So I separate this logically in the following sense. So we integrate the first integral from 0 to 2 pi, then we make a bracket, then we write inside the bracket the inside integral from 0 to infinity, e minus r squared times r. That is the integral of dr. If we did this integral, we get a solution, yeah, and that solution is then integrated for d theta. First, we have now to find the inside integral, and then we do the outside integral. Okay, so outside, we just write it, but we have to care first about the inside. Okay, take a look to the inside integral. What we need to do this integral, we need a variable transformation again. Here the variable transformation I suggest is the following. Well, let's think about. Why not assuming that u u is equal to 2r? Well, I have to think about. Yeah? If no, that's not a good guess. U is equal to r. I think that's a good guess. Let's see about this. What do we have then here? Well, then we have here, well, the integral is from 0 to infinity. Then we have here, if I plug in for ru, we get here e to the power of minus u squared. Right? So, now we have to, wait a second. If we calculate the derivative, no, it's not my preferred guess. This is my preferred guess. U is equal to r squared. I think that works out. Then, for r squared, I write u. That gives me e to the exponent minus u. If I do the derivative, I have du, and here I have 2 times r dr. So instead of r, I write now, bring this 2 over r here. So then I have, well, I have here an r, right? This r times r. And then for dr, I write du 2 over r. Then this r, and that was my intention, cancels out. And here I have 1 over 2, and I can bring the 1 over 2 outside all the integrals. That's a constant. And then what I have to do is just this integral, e to the power of minus u in respect of du. That's, once again, very basic. So what we have now in front, we have the 1 over 2 from 0 to 2 pi. Then my integral d theta. What is the integral of the function e to the power of minus u? Well, let's think about, is it this? If we calculate the derivative of this, we have this function, and then the derivative of the exponent in respect of u is minus. Well, no, we don't need the minus here. Yeah, we need the minus, right? Because we have this, and the derivative is minus 1, right? And then with this minus, we get a plus, and here we have the plus. We need the minus, yeah. And we have to do this integral. What are the limits? From 0 to infinity. So if we substitute the limits in my function, the first element for infinity, it's 0. right? Because this is minus, so its denominator gets large, so the term gets 0. And then we have minus, at, when we plug in here 0, it's 1. So what we have here, this integral, is 1. And now we continue. So what we have now, in front we have the 1 over 2. Then we have the integral from 0 to 2 pi. Inside here we got, this is minus, and now we have to do the integration for theta, right? This is what we, maybe I make here this bracket to indicate that was the integral we did, the inside integral. And now we have to do the outside integral over theta. Well, what is this? Can you tell me this integral over theta? It's just theta at my, well, 1 over 2, right? Don't forget what is in front. And then it's theta at my boundaries, 2 from 0 to 2 pi. And what is this? Well, if I plug in 2 pi here, the 2 cancels, we got pi. And if I plug in 0, well, that's 0. So this integral is pi. But what is what we computed? This is my I squared, right? We call this I squared, and then we moved on here. So we find that I squared is pi. We are interested not in I squared, we are interested in I. But this is easy. Well, if I squared is pi, then this is square root of pi. I think that was the homework. Yeah, basic statistics, how to handle Gaussian density and do integration. Okay. Sorry?
To raise it, to square it, that was the only crazy part. We have to do I squared.
Ah, maybe. I can't remember everything, but yeah. So what we got is that this is I, right? And here from our variable transformation, coming from here, from our fundamental solution, we see we have to care about the 2. So what we have is that the fundamental solution, if we do this integration, we get 2 square root of pi. If we move the 2 inside the integral, I was right? I guessed it must be a 4 probably. I wrote it wrong. So if this integral is square root of 4 pi, but if we now divide this square root by 4 pi on both sides, then this will lead to 1. So therefore we have to correct our fundamental solution. If you go back to the fundamental solution, can I write down the fundamental solution again for x and t? It is 1 over square root of 4 pi dt e s x squared over square root of dt, that was psi, 4 dt, I think, if I'm right. Yeah, so that was the missing 4 pi we were looking for to make my integral of the fundamental solution always 1. And this function here is the famous Gaussian density. It's always positive. The integral adds up to 1, so it behaves like a probability density. So think about it. The goal was to solve a partial differential equation. What we find is a probability density is satisfying the partial differential equation that looks of this form in general. So that gives you the link of a probability density as a solution of a partial differential equation. We know that the Brownian motion, the increments of a Brownian motion, that is what we defined last week, these increments behave also according to this Gaussian density function. And here you can see if the Brownian motion has also this shape, a Brownian motion can be modeled also by a partial differential equation of this type. And that's what we have not discussed, what we will do in one of the next classes. A Brownian motion can not only formulate it in terms of a partial differential equation of this type, it can also be formulated into a so-called stochastic differential equation. Yeah, but if the stochastic differential equation leads us to the same density, and density is linked to this, you see stochastic differential equations will be linked also to so-called partial differential equations. So the last topic of the day is to show you the linkage of a heat equation and a Brownian motion explicitly. Now that is what I want to show you now in the final lecture time explicitly. That is my last point.